So in the previous lectures we have studied about the basics of heat transfer. That is, we had simply a basic idea about conduction, convection and radiation. Now today we will simply start with the very first topic in heat transfer, that is conduction. Okay. Now, as I have discussed, that conduction is a mode of heat transfer in which the heat is being transferred from one molecule to the other by means of free electron transfer, which accounts for about 70% of the total heat transfer, and molecular lattice vibrations, which accounts for about 30% of the total heat transfer. Now, in the conduction topic, we have to mainly study the conduction of heat through slabs. They can be simple and composite slabs. Okay. Next, through cylindrical wires, for example wires we have, and they can be simple as well as composite. Next is spherical systems. They can be simple or composite. Composite systems simply means that thermal conductivity for different sections will be different. For example, in one section we have used glass wool and in the other section we have used asbestos. So the thermal conductivity will be different for both the sections. Okay. Now I'll start with the very first, that is conduction through a slab. Okay, now we have the case of a slab such that it has two faces. One face is at the temperature T1, the other is at a temperature T2, such that T1 is greater than T2. Okay, and the heat is being transferred from T1 to T2 because we have studied in the law of conduction, in the Fourier's law, that heat always travels in the direction of decreasing temperature. That is in the direction of negative temperature differential, that is dt by dx should be negative. So at this phase, so for example, if the width or the thickness of this slab is b, then the coordinate for this phase will be x is equals to 0, and the coordinate for this phase would be x is equals to b. Now if we talk about the boundary conditions, at x is equals to x0, t is equals to t1, and at x is equals to b, t is equals to t2. This is the general boundary conditions that we are applying here. Now writing the Fourier's law, qx is equals to minus ka dt over dx. Okay, this is the general Fourier's law. Now dx will be multiplied by qx multiplied by dx is equals to minus ka dt. Now we integrate from x is equals to 0 to b, and here from t1 to t2. Now solving this equation further, we will get q into b is equals to ka t1 minus t2. So this actually gives you the rate of heat transfer through a slab. Rate of heat transfer through a slab. This will give you the rate of heat transfer through a slab, and this is nothing but it is actually Fourier's law. This is actually the Fourier's law, and it will be in heat will be in watt. Heat transfer will be in. One very important point which is to be noted here is that Q is actually not a function of X. The heat which is being conducted is not a function of the coordinate X, because there is no heat generation, or accumulation of heat. No heat generation and no accumulation, and therefore we can say that Q is not a function of X. Now in the formula, the area which is being used here is actually the area which is normal to the direction of heat transfer. This I have already explained in the previous lecture when I was discussing about the basics of heat transfer. Okay, so this area is actually the area which is lying normal or perpendicular to the direction of heat transfer. Now one very basic difference between the word perpendicular and normal. What is the difference between these two words? Actually, they both mean the same, that is normal or perpendicular both means the line or the segment is making an angle of 90 degrees, but the basic difference is normal word is actually used in the 3-dimensional sense and perpendicular is used in the 2-dimensional sense. Now, for example, now if we divide this area with Q, for example, Q upon A is equals to K T1 minus T2 upon B. So this becomes the unit of, this is watts per meter square, and this is nothing but it is called as heat flux. This is called as heat flux. Now here we have an analogy between the heat transfer and the between thermal and electrical states. For example, in the electrical terms, the current is represented by I, unit is ampere. So this corresponds to the analogy of heat which is flowing and the unit is watt. In electrical system, we have the EMF or the electromotive force or change in the potential difference, which is denoted by, or it is manifested by, the change in temperature, and the unit is Kelvin. Here we, in the electrical terms, we have resistance and the unit is ohm, whereas this when manifested in the thermal terms becomes the R thermal, or the resistance of the thermal material, or the resistance which is offered to the flow of heat. Now, if we draw the electrical circuit versus the thermal circuit, for example, if this point is 1, this point is 2, and this is a wire such that this is the electrical resistance and the current is flowing is I, such that the potential difference between these 2 points is delta V. So we write V is equals to IR according to the Ohm's law, then R is equals to delta V upon I ohms. Now, in the thermal analogy, we have the point, say this is at temperature T1, this is at temperature T2, so delta T means T1 minus T2, and we have seen that temperature or delta T corresponds to the change in the potential difference. So we have written delta T upon Q. Q corresponds to I. So delta V corresponds to delta T and I corresponds to Q. So this becomes R thermal conduction. So if we see, then R thermal conduction becomes T1 minus T2 upon Q. This becomes the R thermal conduction, and if we find out the value of T1 minus T2 upon Q from this formula, we will get that T1 minus T2 upon Q is simply equals to B upon Ka. B upon Ka. So this is actually the R thermal conduction resistance. It is also called as conduction resistance, and the unit will be, what will be the unit of thermal conduction resistance? It will be delta T upon Q, that is Kelvin per watt. The unit will be Kelvin per watt. Please mind the units, because units are very important. 1 marks direct questions can be asked in the examination. Now, in this case that we have discussed, there was just one slab having a thermal conductivity of small k. Now, for example, if we make this as a composite slab such that we have one more slab which is adjacent to it and having some thickness, say B2, and this has a thickness of B1, such that the composite slab which is next to it has a thermal conductivity of K2. Now, let us look at the example of that. Now this is the composite slab such that it has such that the first slab is having a thickness of B1, the other is having a thickness of B2, and they are joined to each other such that one face is maintained at a temperature T1, the interface is maintained at a temperature T2, and the other side face is maintained at the temperature T3. Now there are certain assumptions which are common to all the problems, and these assumptions are: there should be a 1D heat transfer. There is 1D heat transfer, that is, heat is being transferred only along the X direction, Then next we have, there is a steady state. Now if we draw the electrical resistance circuit for this type of diagram, it would be, this will be temperature T1, this will be the RTH corresponding to this slab 1, okay, then this will be temperature T2, and then we have another resistance, and then we have temperature T3, and this resistance will be RTH corresponding to the slab 2. Okay, so RTH1 becomes B1 upon K1A, and RTH2 becomes B2 upon K2A. So this is the thermal conduction resistance corresponding to this slab, and this is the thermal conduction resistance corresponding to this slab, and heat is being transferred like this. A is the area which is common to both, which is very simple. Okay, now if we write according to the law, if I need to write down the equation for the conduction of heat, what will I write? Q equals T1 minus T3 upon B1 upon Ka plus B2 upon K2A. Current is equals to voltage difference upon resistance, or we can write current is equals to voltage difference upon resistance, such that this resistance is actually the effective resistance of both these slabs, that is R1 plus R2, because they both are connected in series. Now this is a very simple equation which can be easily solved. For example, in the numericals we are asked any value. For example, what is the K1, what is the conductivity, thermal conductivity of this slab K1? It can be asked such that all other values will be given. For example, if heat flux is given, it means the value of Q upon A has been given, watts per meter square will be given. Now generally in such problems, the temperature of this interface, that is temperature T2, may be asked. Now that is very, very simple to find out. Please understand one logic, that the amount of heat which is going through this phase will definitely pass through this phase also, and will be eventually passed through this phase also. So if I write the heat transfer between the temperatures T1 and T2, if I neglect this slab, then heat will be transferred between only two phases T1 and T2. So I will write Q is equals to T1 minus T2 upon B1 upon K1. Okay, now if I neglect this slab and write the heat transfer equation between the phases T2 and T3, it will give me Q equals T2 minus T3 whole upon B2 upon K2A. Alright, so we know that this Q and this Q are equal. These both are equal. So by equating these two equations, the value of T2, which is the interface temperature, can be found out. Now while solving these problems, we can also encounter convection thermal resistance. We will also encounter convection thermal resistance. Now what is convection thermal resistance? If we remember the Newton's law of cooling for convection, then we will find out the equation that we wrote, Q is equals to HA T surface minus T ambient. Alright, now we know that R is equals to delta T upon Q. So if I write R, it will be Ts minus T infinity upon Q, which will be equal to 1 upon HA. So 1 upon HA actually becomes R thermal convection. R thermal convection. This is the unit for thermal resistance in case of convection. Alright, and this will have also a unit of Kelvin per watt. This will also have a unit of Kelvin per watt, this R thermal convection. Now one very important point which is to be noted here is, as the area is increasing, since R thermal convection is inversely proportional to area, so as the area of contact is increased, its thermal resistance for convection will definitely decrease. Okay, this was a very important point which is to be noted here from this formula. Now if we come to a case where there are composite slabs such that on left hand and the right hand side faces of these slabs we have convection through the gases also. Say for example, if Q amount of heat is being convected off from this hot gas to the phase T1, it will then travel to T2, then to T3, and finally it is convected off to the ambient surrounding. Now if we draw a thermal resistance circuit, how will it look like? First, temperature is, for example, temperature of the gas is Tg, so this is 1, this will be Tg, this will be T1, this will be T2, this will be T3, this will be T ambient. The value of this resistance would be 1 upon H1A, where H1 is the convection heat transfer coefficient of the hot gases. Now between T1 and T2 what do we have? B1 upon, say conductivity is K1, conductivity is K2, K1A. Now between T2 and T3 we have B2 upon K2A. Now between T3 and T infinity we have 1 upon H2A. So this is the thermal resistance circuit that we have made from the diagram above. Now if I need to write down the equation of heat transfer from this circuit diagram that I have made, that what will I write? Q is equals to Tg, but we always write the equation between the extreme temperatures. Okay, extreme temperatures, Tg minus T infinity whole upon 1 upon H1A plus B1 upon K1A plus B2 upon K2A plus 1 upon H2. So this will be the equation for this diagram that we have discussed here. So this equation is applicable for finding out any unknown quantity if you encounter through this formula. So if we are asked to find out the heat flux, it will be Q upon area, that is watts per meter square. Now we will introduce one new term, that is overall heat transfer coefficient. Now overall heat transfer coefficient is nothing but it will simply encounter, or it will include all the resistances which are being encountered in any problem, and it is represented by the symbol capital U. So instead of writing Q is equals to the entire formula, we will simply write Q equals UA delta T, or UA Tg minus T infinity. Alright, where U is the overall heat transfer coefficient, which takes into account all the modes of heat transfer. It takes into account all the modes of heat transfer, that is, it takes into account conduction, it takes into account convection. Alright, it takes into account of both these heat transfers. Now in this lecture we will simply discuss the entire theory of conduction, and in the next lecture we will be solving only problems relating to the theory that we have studied. Now we come to the case of conduction of heat in case of a hollow cylinder, that is heat transfer in case of a hollow cylinder, such that the inner radius is R1 and the outer radius is R2. The inner temperature surface is maintained at a temperature of T1 and the outer surface is maintained at a temperature T2, such that if we write the boundary conditions, then we have at R is equals to R1, T is equals to T1, at R is equals to R2, T equals T2. So these are the important boundary conditions. These are the important boundary conditions, and we will see that the heat is being transferred radially outwards. Say for example, if this inner pipe or inner segment is carrying a very hot liquid or any fluid which is at a very high temperature, so heat will be given out in the radial outward direction. So we have the radial distribution of heat. Here we have T1 is greater than T2. In the previous diagram also I have assumed that T1 is greater than T2. Now we will note that temperature gradients are along the radial direction, so there will be a radial conduction of heat outwards, that is from the inner cylindrical surface towards the outer cylindrical surface. Now if we see that in case of, for example, the length of the cylinder is L, if the L is the length of the cylinder, so area encountered during heat flow would be what? It will be 2 pi RL. The area encountered at any point would be 2 pi RL, where R is the general radius of the cylinder. Now again, if we write Fourier's law, Q is equals to minus Ka dt over dx. Okay, now we don't have x, we have r, so I will write dt over dr, and this is qr, such that I will replace area is equals to 2 pi rl. So we have qr is equals to minus k 2 pi rl dt over dr. Now I will take r and dr on the left hand side. It will become qr into dr by r is equals to minus k 2 pi l dt. Now simply integrate both the sides, t1 to t2, and this side r1 to r2. Now on solving this equation, I will directly get, and I am writing the results, q ln r2 r1 is equals to 2 pi kl T1 minus T2. So if I write Q equals to 2 pi KL T1 minus T2 upon ln R2 by R1. So it can also be rearranged into form of Q is equals to T1 minus T2 whole upon ln R2 over R1 divided by 2 pi KL. So this is the expression for the heat transfer in case of cylindrical systems. And if heat per unit length, and if heat per unit length is asked, then we will calculate Q by L. Okay, so from here we can get the expression for heat conduction, such that this quantity, the denominator, entire denominator will be R thermal conduction for cylindrical systems. Now K, as we already know, it is the thermal conductivity of this cylindrical material that we have taken here. Now the thermal conduction resistance for the cylindrical case would be ln R2 over R1 upon 2 pi K. Alright, that we have derived here. Now say we have another very important case of composite cylinder, such that the innermost radius is R1, the next radius is R2, and the next radius is R3, and the temperatures corresponding to those segments will be T1, T2 and T3, such that T1 is greater than T2 is greater than T3. Alright, now as we know, heat will be radially conducted outwards. Now if I wish to write down the electrical circuit for this type of composite cylindrical slab, then that would be T1, this becomes T2, third resistance, this becomes T1, T2 and T3. Now while moving from T1 to T2, we counted two radiuses, that is R1 and R2. So resistance would be ln R2 over R1 whole upon 2 pi K1. Say for this we have conductivity K1. For this we have conductivity K2. Now ln R3 over R2 whole upon 2 pi K2L. L will be the length of the cylinder. Now while moving from point 1 to point 2 we have ln R2 over R1. Now when we move from point 2 to 3 we had R3 upon R2. So this is the resistance, total resistance in case of cylindrical case that we have obtained here. Now if I write the equation Q, that will be T1 minus T3 whole upon ln R2 over R1 upon 2 pi K1L plus ln R3 upon R2 upon 2 pi K2L. So this will be the equation for heat transfer or conduction of heat in case of a composite cylinder. Okay. Now if we have a case of convection and conduction both in case of this cylindrical system, such that the innermost pipe is being supplied with a hot gas, such that the temperature of the hot gas is Tg and the convection heat transfer coefficient regarding to it is Hg, and the temperature of the innermost surface is T1, then we have T2, then we have T3, and finally the temperature of the ambient is T infinity. Okay, now we will see in this case also that the heat is being conducted radially outwards. Now let us write down the circuit for this diagram and then we will write down the equation for heat.